Okay, don't know why that was cut off. So I'm going to answer this question because I'm pretty sure everyone has the same question about the NMR, the mass spec, and the IR, so I'll just go ahead and answer that. There are two types of NMR. We'll start with the NMR. Two types of NMR, the 1H and the carbon-13. You don't need to know the carbon-13 for this exam. It's oddly omitted, but carbon-13 we can definitely talk about really quick. With 1H NMR, there's three pieces of information. Get out the chemical shift, the delta, the area, and multiplicity. So some instructors emphasize this being able to take the spectrum and be able to write the molecule. That is a terrible, terrible approach to work with life, and it also, fortunately, is not what this exam does. So what you're better able to do is be able to figure out, based on the molecule, what do you expect to see in the spectrum. So if you're given, we'll start with a simple 2-pentone, and you're asked, okay, is this molecule consistent with the 1H NMR? The first thing you need to do is tweeze out how many different chemical shifts you expect to see, and this is looking at symmetry. So if you look at 2-pentanone versus 3-pentanone, this should have 1, 2, 3, 4 chemical shifts associated with it. Because the mirror plane is sitting here, we have 1, 2 chemical shifts in this molecule. So we expect to see 4 chemical shifts for this one, 2 of this, and this is by rotation or mirror image. So if you can rotate the carbon bond and they look the same, they have the same chemical shift. If you can take a mirror image, they have the same chemical shift. So chemical shift, the first thing you should tweeze out. Area is the next thing. It's just the number of protons. So this we expect to have an area of 3, 2, 2, 3. This should have an area of 3 and 2. For the 1 and 2, it's always the simplest ratio. Yeah, I know the light's kind of in the way. Oops. That might be bright enough. And then the last thing to work out is multiplicity. And multiplicity is the number of nearest neighbors with the same chemical shift plus 1. So if we look at 1, there are 2 hydrogens next to it, so this would be a triplet. 3 here has 2 hydrogens next to it, it would be a triplet. This has 3 next to it, so that'd be a quartet. And then these 2 here, which would give you a triplet, and this would be a singlet. This here would be a triplet, and this here would be a quartet. So this is the more useful way of doing 1H NMR, is predicting the spectrum. Now, when it comes to trying to do this rapidly, so if you're given multiple molecules and you're asked which of these is consistent with the 1H NMR, the thing I always recommend is hunt the singlets first. The singlets are the easiest to identify. So a singlet comes about because you have a carbon that is isolated from all the other hydrogens on the carbon, isolated from all the others. So these are typically going to be methyl groups. Sometimes you see bridging CH2 groups. But generally speaking, the singlets are the easiest to see. So figure out if your molecule has a singlet or not. If your spectrum doesn't have any singlets in it, you can eliminate all the molecules that are generating singlets. Conversely, if your signal does have a singlet, look for which molecules don't have singlets, get rid of those, and then start counting the areas. And 9 times out of 10, that will get rid of at least half the options for you. And then start working in the more complicated ones. Look at terminal groups. So look at things like terminal methyl groups that are adjacent to something. You should see a triplet or a doublet depending on how many hydrogens are near. Now, carbon-13 is simpler. It's just simply not on this exam. It's the number of carbons that give rise to a chemical shift. So we have 1, 2, 3, 4. So the number of unique carbons. We have 3 unique carbons in this molecule. Now, carbon-13, we're going to update this for the fall. Carbon-13 is quantitative in principle, but it's not quantitative in practice. So we treat carbon-13 spectra as if they are quantitative. It's really kind of a nuance of how long it takes those nuclei to stand back up. In practice, it's prohibitively long, therefore expensive, because you pay by the hour with NMR to do quantitative carbon-13. So the only thing they do is they look for the number of chemical shifts, but they don't look for the relative areas. Again, interesting facts, but not really something you need to know. Now, infrared spectroscopy. You got your transmission and you've got your wave numbers. And what FTIR, Fourier transform infrared spectroscopy, is going to tell you is the functional groups that are present. Now, again, some instructors like to say take the spectrum, predict the molecule. That's not particularly useful because there isn't a uniqueness theorem with IR unless you're looking at the fingerprint region, which we don't do. So the more useful thing to do when approaching IR is to say, what functional groups are different between the two molecules. So if you look at, those two will give the same spectrum. So let's say we had 3 pentanol and 2 pentanone. Both of these contain CH3, CH2 groups. This isn't particularly useful to go hunting for those spectrum. In fact, all organic molecules contain those bending modes. And for all of them, you should kind of see about 3,000 this kind of little jagged set of peaks. They're not particularly useful because they all have them. The big difference here is the OH group and the ketone. These do have specific bending modes. So what you do with the alcohols, you would look for a big broad peak at 3600. And off the top of my head, I don't remember what the ketone bending mode is. But what you will be given a table of common IR bending modes. So identify what functional groups are unique to this given molecule that you're looking at and see if that peak is present in the spectrum. Now, a challenge with IR, and this is admittedly what makes it a not so great technique for identifying compounds, is particularly by functional groups. There's a lot of functional groups that share overlaps. So we try to keep those examples away from you, but definitely something like cis versus trans. In principle, with IR, you can figure that out, but their bending modes are really close, so it becomes a really kind of a challenge. And also, if you have a benzene ring that also has alkene bending modes in it by the fact that a benzene ring has alkene groups. So again, big thing is looking for huge differences between the molecules and peaks where one molecule should have them but not the other. Now, mass spec, we do a horrible job of assessing on this. It's simply because we don't have the ability to let you look things up by database. With mass spec, what you're looking at is the weight of the parent ion. So we do electron ionization, mass spec. We look for the parent ion, and this is pretty much the mass of the molecule. Now again, this is kind of really insulting to the technique because the technique can give you a lot more information than that. But what you can do is you look for the last highest peak. So let's say you're given a mass spectrum, and you don't care about these little peaks at the front. These are just isotopes, and so what we do is try to choose out the highest one. And this will give us an idea. If we have molecules that are different sizes, meaning different numbers of carbons, hydrogen, oxygens, this is a pretty good way to resolve it. You never really have to kind of deal with, like, we wouldn't use this for something like between an alcohol and an aldehyde. So if you do a reduction reaction, an oxidation reaction of an alcohol, and you only get rid of 2 hydrogens, yes, mass spec can see that. It's just kind of picky and nuancy. 1710 to 1750 sounds about right. I don't generally memorize these modes. Alcohol I only know because that's actually a water contamination with silicon dioxide. So when I did aluminosilicate research, that was indication that you had water, and it was really hard to even explain to the PI that 3600 is not water, it's hydrogen bonding mode. So that's why I know that one off the top of my head really well. I don't know many of those. The other is the, I think it's the 2200 carbon dioxide. It's a really distinct peak if you've got carbon dioxide. Complicated Diels-Alder problems. So we can go over complicated Diels-Alder. I will say you're going to see some very symmetric. We're going to kind of keep the complicated ones off the exam. There's going to be Diels-Alder, but definitely like nothing super intense. So any basic Diels-Alder reaction, you're going to form cyclohexene. And if we look at our parent molecule, we've got 1, 2, 3, 4. And I do alpha and beta on mine. And the way you remember, alpha and beta are always opposite the double bond. So when we finish, we should end up with a, yes, both 151 and 152, you're provided with the IR bending modes. I do not see a point to making you memorize those. When I took undergrad, they threatened to make us memorize them. Books exist for a reason. But yeah, you're gonna get the exam. This should be available on the course website, the final exam packets or the final exam test tables. So you're given common chemical shifts, common bending modes for IR. You're given. Let me look up on the website really quick. I'll get back to the Diels-Alder question. Did I not post it? Well, that seems mean. So anyway, with Diels-Alder, what we typically try to shoot for are symmetric. So if we have this as our Diels-Alder, first thing we do is we draw the cyclohexene, and then we put whatever's attached to these groups. So let's say I have isopropyl, isopropyl. So carbon 1 is going to have an isopropyl group. This is going to have an isopropyl. This will have a methyl, and this will have a methyl. So how does this get hard? Well, let's say it's asymmetric. So alpha and beta both have a methyl group. Well, we can conceive of a scenario, so we'll draw out our cyclohexene group. One's going to have the isopropyl, and then 3 is going to have the methyl group, but we can attach alpha and beta either so alpha's up or so alpha's down. And we'll end up generating two possibilities here in terms of how they come together. So this is the challenge with asymmetric Diels-Alders, that you inherently end up with this mess of a whole bunch of different constitutional isomers by sheer merit that you can rotate this 180 degrees or you can rotate this 180 degrees. Now in truth, you should really only be able to get two possibilities, but again, you can kind of get a mix with these. Wittig reactions. So Wittig reaction, the mechanism is super complicated, the end result is not. So with your Wittig reaction, if we have any type of ketone, and we have our Wittig reagent, and so R here is whatever is attached, you're given the Wittig reagent, so whatever is attached to it, this R group, basically the shortcut for Wittig, cut off that double bond, and whatever the R group here is attached to phosphorus, that's now double bound to the wherever that ketone was. So with the Wittig reagent, again, you're not going to have to worry about prepping Wittig reagents. The book goes into a lot of length of this. I think even the notes go into a bit with the Wittig. You don't need to worry about prepping the Wittig. The way the Wittig works is you start with triphenylphosphine, and then you have to have your iota group. The triphenylphosphine pulls off the iodine. This results in a double bond. Yes, if you end up with, actually, if you were given a complicated one, you would have to worry about like giving both answers. That said, it's the final exam. We're not going to give you asymmetric Diels-Alders. They're going to be symmetric, so there's only one possible answer. But with the Wittig, again, you don't need to know this. You're not making Wittig reagents. But let's say you were given this as the R group that was attached to the Wittig. That's just what would end up being double bonded to it. Mixed aldol addition and condensation. Okay, aldol addition condensation. Again, we're going to keep the exam pretty straightforward in this regard. But there's definitely like nightmare scenarios here. So this would be like the absolute worst, is that you have two different asymmetric alkenes. Tollens and Benedict's. Tollens and Benedict's. Tollens is used specifically for the test of aldehydes, and then Benedict's is used for the presence of sugars. So Tollens is specific to aldehydes only. Benedict's will test for both aldoses and ketoses, but again, this is the test 5 material, so I'd say you don't need to worry too much about the Tollens and the Benedict's. So this would be an absolute worst scenario here, because you're going to end up generating a whole mess of products. So the question is, who's the nucleophile? So we can do one where this is the nucleophile, and we can do one where this is the nucleophile. So if this is the nucleophile, it can attack from here or here. And if this is the nucleophile, it can attack from here or here. So do the aldol addition first, because you always end up with the aldol condensation just being an end result of the aldol addition. So this is going to attack this carbonyl. That's going to attack that carbonyl. What did I just draw? And then for this one, same thing. This is going to attack that carbonyl, so we can get one. Oh wow, this is so big. Oops. There and there. Let's see if you can still see that. Yep, down there. It's hard to see, but it is there. So these are all the aldol addition products for two asymmetric ketones with two alpha carbons that are acidic. So you have to work out both scenarios, one where this is the nucleophile, one where this is the nucleophile, and then you have to work out for each one where each alpha carbon attacks, and that will give you the condensation. Now, or the addition. The condensation occurs if you have any acid or base, particularly if you have any acid left or base left, and quite frankly, that's what you need to catalyze the reaction, so it typically is there. And what will happen is that if there is still an extra hydrogen left on the alpha carbon that did the attacking, you'll get elimination to get the alkene. Now with these, keep in mind, if you see 5 bonds around carbon, then you weren't able to actually do the condensation. So those are all the condensation products. Now, one thing we don't talk about is that you saw this with Adil's Alder Lab where it actually went around and did it a second time. So not only can these do this first aldol addition, now you've created a whole bunch of alpha beta unsaturated carbons that are now able to move on and do reactions with themselves. We're not going to consider subsequent reactions. Again, exam's going to kind of keep it focused to more where there's really only one outcome. We need to be familiar with aromatic compounds. Not identifying aromatics, but you do need to be familiar with reactions of benzene rings. So how groups are added to them and how those groups direct subsequent groups. But as far as identifying if a molecule is aromatic, I don't think that's really on there. I could be wrong, but I'm pretty sure it's not on there. Wish it was. Maybe in the future. Yeah, you're welcome. Directing groups, sure. So reactions of benzene. So we'll start with reactions of benzene, then we'll move to directing groups. So nitration of benzene is one that really is just genuinely a useful reaction to know. Comes up more than it should, honestly, for what it is. This adds an NO2 group. You can do straight sulfuric acid. I personally think this is a pretty dumb reaction. We have Friedel-Crafts, and there's two types of Friedel-Crafts. There's the alkylation, and this is where you add an R group, but the thing is the R group has to be secondary or tertiary, because what you will go over with, what will happen with Friedel-Crafts is you go through a carbocation intermediate at the halogen. So let's say we have this 2-chloropropane. This will be fine, but if we try to do it with this, we'll get carbocation rearrangement. So this is the alkylation. The acylation is this reaction here where we end up where we have the chlorine attached to a carbonyl. This doesn't permit carbocation rearrangement. But they both involve AlCl3, and you get, for alkylation, you get direct attachment wherever the halogen is, assuming it's a secondary or tertiary. And for the acylation, you get attachment at the acyl group. Now, also with AlCl3, we can do AlCl3, we can do FeCl3, FeBr3. These are halogenation reactions. So if you have a halogen, a respective iron salt, and I think you can also do these with the aluminum salts as well, you get chlorination or bromination. And then I think those are the big ones. Yeah, those are the most common benzene ring reactions. There's probably one or two I'm missing. Like, you don't need to know Birch reduction, the one where you take you use sodium and you end up generating like the cycloalkane from benzene. Such a worthless reaction. So, how do these groups direct? So, this is a meta-director. This is a meta-director. Ortho-para, meta, and you've got books debate this. This is actually ortho-para from my understanding. So the way you figure out the way you can look at it and tell if it's ortho-para or meta. So ortho-para is going to be either alkyl groups or one where the ring attached to the benzene ring has lone pairs. And this is a resonance stability argument. So if we have alkyl groups, so like CH3, isopropyl, anything that's just carbon and hydrogen, those are ortho-para directors. If we have something like nitrogen with a lone pair, oxygen with a lone pair, or halogens with lone pairs, these will be ortho-para directors. Well, now, these two in particular are kind of debated in books, especially the latter. This has lone pairs that stabilizes the ortho-para position, but they're also electron withdrawing, so they tend to slow the reaction down. R3, I'll get to that in a minute. So, meta-directors. These are typically halogenated alkyl groups. Anything where there is a carbonyl by the ring. So if we have this, if we have benzoic acid, if we have like an aldehyde, these are all meta-directors because the carbon is getting all the electron density pulled off of it. So how do you decide what happens next? So let's say we have an R group, something attached to it, and it's an ortho-para director versus a meta-director, and we're going to add, we'll say, a nitro group. So the thing to keep in mind here is that this does not care what you're adding to it. The only thing that matters, the only thing this tells you is what you're adding to the ring. This tells you where you're adding. If it's a meta-director, you'll get out of there. If it's ortho-para, you'll get it at it in the ortho or para positions. Now the way I remember ortho-para, ROMP, R-O-M-P. Now, this will be the majority product by sheer merit of sterics, but you will produce both products, particularly if R is not a big group. So if R was like tert-butyl, you'd exclusively get this. If your R group was toluene, you would definitely get ortho-para positions. Chair confirmations, Fisher-Haywoth projections. Yeah, again, that's kind of like the test, the review packet material would say you definitely probably don't need to focus too heavily on Fisher and Hayworth projections. Except one for exam 4 notes with RCOH plus and the RC3 group attached to the benzene. Can you explain? So this is kind of... So the way Friedel-Crafts works, so I'm bringing up Friedel-Crafts for a reason, is that you actually end up generating a carbocation and an aluminum chloride salt. This aluminum chloride salt is what's attacking the benzene ring. So the benzene ring is very electron rich. And your carbocation here will attack it. It'll temporarily break the aromaticity of the ring. And then we end up getting a hydrogen back. I'm trying to remember how we do this. Oh, so the chloride, this will be the weird one. The AlCl4 will abstract this hydrogen and then put it back here. And that's how we end up adding it to the ring. So we create a carbocation with the Friedel-Crafts acylation agent or alkylating agent, the AlCl3. And this is actually what happens with iron bromide and iron chloride. They end up generating a carbocation, and that's what attacks the benzene ring. And this is true if you work out for all the reactions of benzene. You're always generating some positive group. So for HNO2 or HNO3, H2SO4, when you do the nitro, you're forming the nitronium ion, the NO2+. That's what's attacking the benzene ring. So why does this work for the alcohol? So here we've got the Friedel-Crafts reagent generating this carbocation. For tert-butanol and phosphoric acid, you actually end up protonating this, and that can come off. So what this will do is it'll protonate the hydrogen here, give you an OH2. That'll pop off, and that'll give you the carbocation. And that carbocation subsequently reacts with the benzene ring to give you the addition. So it's kind of like a halogen-free Friedel-Crafts reaction. And it is kind of interesting, like this is all part of a broader class of reactions, but it's one of those how to teach it to you. Basically all benzene reactions are forming a cation of some sort and using that to attack the benzene ring, but if I present it that way, you may kind of get lost in the mechanisms of how these carbocations are generated. That said, if you understand it's pretty much all generating carbocations, suddenly like these later reactions start making a lot of sense. You're kind of seeing it's just one of those things like you got to start somewhere. I prefer just teaching the overall reactions first, and then we can start digging into the mechanisms down the road. But definitely trying to understand it all at once just isn't possible. And yeah, I kind of noticed this the more and more I'm teaching this course, the more and more these reactions are starting to make sense. But I can definitely see how, like 2 years ago when I just started teaching the course and was still kind of relearning it, how easy it is to miss a lot of this information because it is a lot to take in. Good questions. We need to know reactions using organic metallic compounds. Be familiar with the Grignards and the organolithiums. You're not going to need anything that's transition metal catalyzed. So anything that involves anything from the D block, this particular exam tends to omit a lot of that, which I think is weird. But whatever. We're changing the exam this fall. But yeah, know your basic organometallics. With organometallics, it's always the same. They all look different. They're not. What you're doing is you're generating a carbocation that's attacking some type of carbonyl. And it's just a matter of how you're generating this. So one way is you can take an alkyl chloride and add lithium, and that'll give you your carbanion. You can start with an alkyl bromide, add magnesium, That'll give you your carbanion. If you have a ketone and add a hydroxide, this will also give you your carbanion. So we could have something like this and add hydroxide. All of these are just different ways of creating carbanions in solution. And then attacking that. Do we need to be familiar with kinetic and thermodynamic products? No, I don't really think you need to worry about kinetic or thermodynamic products. I don't think it shows up at all in this exam. In general, I would say it's useful to know, but no, I would not say that you need to know it for this exam. I don't think kinetic and thermodynamic show up. The Heck reaction. Nope, don't need to know the Heck reaction. Again, it's weird. Like the transition metal stuff is like not being assessed on this exam. I think the Heck reaction is really useful, but the Heck reaction, yeah. So I can go through the Heck reaction. So the Heck reaction, you always have some type of terminal bromide, and you've got a terminal alkene. And this is palladium catalyzed PdOAC. The OAC here is acetate. That's just to solubilize the palladium. We don't go through the mechanism of this in this course. You actually need to take inorganic chemistry to know how this works. But pretty much it just clips the bromine bond and attaches the two double bonds together. So that's the summary of the Heck reaction. You have an alkene bromide, terminal alkene paired with a palladium catalyst, and this ends up generating these conjugated. And then epoxide. So epoxides, again, we're going to stick to symmetric, so there's really only one answer. So with epoxides, you would have to worry if we were going to do asymmetric whether or not, do we know the concepts in the final exam PowerPoint like carbonate? No, I would say it would be an utter waste of your time to go through and learn that. Not so true this fall, but definitely I would say these are not particularly useful reactions to know. So with epoxides, it's just an HX addition. With the HX addition, and the X comes in from the bottom. X here can be a lot of things. So X can be NH2, so we can add ammonia to it. It can be a chloride. It can be H2O. We can do a water opening of ring epoxides. Anything that you can add across an alkene, you can add to a epoxide. Also, anything that has a negative charge. So for any carbanion, carbanions will do the same thing where they attack and they end up just being a nucleophile. I think you will be very intrigued by the final, Madison. And it is a multiple choice final, so keep that in mind. Like, do process of elimination. If you're not sure, eliminate the ones that are obviously wrong. So if you got to guess, at least you're guessing with the odds in your favor. Enol is most stable. So enol stability, so we'll just go over it really quick. Enols are formed when you take an aldehyde or ketone and you tautomerize to give you an alcohol, which is adjacent to the double bond. This is generally speaking the more stable form. So the way that you make it more stable to do this is to stabilize this alkene. And the first way is conjugation. So we'll just put an R here. So if you can create a conjugated system, this ends up being much more stable because you end up creating a conjugated pi network. If we get rid of that double bond and move it here, now we just have 2 pi bonds. But if we do the enol, we end up getting 3 pi bonds on the line. The ultimate finish to this is aromaticity. So aromaticity requires conjugation and it requires a ring network. So if we put 3 double bonds, Robinson annulation. I wouldn't worry too much about Robinson annulation. So once you get aromatic, there is no reason to break aromaticity. There is nothing about this that could possibly outweigh the benefits of being in an aromatic ring. So Robinson annulation. So for Robinson annulation, this is a finish up to the Michael reaction. And the Michael reaction, there are lots of forms of it. This will be the most common Michael reagent just because it's the easiest to find and use, and also it's just a really nice example. But the way to think about the Michael reagent is that it's HX. And X is this big molecule here. So with the Michael reagent, what we're doing is we're just doing an HX addition across a double bond that happens to be adjacent to something that's very electron withdrawing and something that can engage in resonance with this double bond. So we can definitely like resonate this ring to make that. So the driving force here is that you need something that's really good at pulling out electron density and really, really good at stabilizing any lone pairs that are formed here. So if I just said do an HX addition across the double bond, especially with X being very sterically hindered, you'd write that. So that's all a Michael reaction is. It's just a glorified alkene addition where X is a very big group that ends up being forced to the very end away from the double bond or away from the carbonyl group or nitro group, whatever's stabilizing for it. Let's see if we can carve down. And now you're left with this molecule. So I need to draw an extra methyl group here, otherwise this won't work. So the driving force for the Robinson annulation is a 6-membered ring. So what we do is we start cutting out from a carbonyl 1, 2, 3, 4, 5, 6. So it's only if we have an alpha hydrogen here can we do this, but this is just an internal aldol condensation. So this will attack this, and again, we're going to keep it simple with symmetric. And if we draw our 6-membered ring, we'll number this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Carbon 1 is our methyl group, carbon 2 has our carbonyl, carbon 3 has nothing on it, carbon 4 has this methyl group, carbon 5 has this group, and we attack carbon 6 to give us this. Now, if we can, we'll also further undergo an aldol condensation. That's just Robinson annulation. It's the Michael reaction, but you happen to have a couple of carbonyls here that make it really favorable to do the attack, and so you can drive the aldol condensation. How would you identify which carbon is most acidic on a compound? So acidity is basically established by how close you are to a ketone and how many different resonances you can create. So if we pull a hydrogen off here, the question is, can this lone pair go anywhere? In this case, it can. It can form the enolate. So this would be more stable than something like a propyl group, because if you take a propyl group and you make the lone pair, it's kind of stuck there. So this carbon feels this negative charge and can't do anything about it. Now, if we add another group here, this ends up becoming more acidic by sheer merit of the fact that it's got 2 resonance options. So it can either resonate with the one on the right, or it can resonate with the one on the left. So basically, how adjacent you are to a lone pair or a carbonyl carbon, because you can do the same thing with double bonds. If we put a lone pair here, this can kick over, and we can resonance stabilize these. The more adjacent double bonds you have to yourself, particularly if you have carbonyls to pull electron density off, that's going to increase the acidity. Protecting groups for amines and ketones and aldehydes as well. So your protecting groups for ketones, these will fall underneath the acetyl and acetyl and hemiacetyl categories. So the first thing you ever form, you need an ROH group. First thing you form is an alcohol ester that our Jason shows. This is your hemiacetyl, and then if we add another alcohol, we get kind of this diether. Ideally, these R groups are connected, and so you'll see sometimes ethylene glycol written, and this can only form the acetyl. So those are your predicting groups for amines, basically, or ketones and aldehydes. It's just an alcohol that's added as a way to protect the group, to make it into something that can't be removed. So it's really hard to pick off ethers. In general, ethers are pretty boring molecules. They don't really do that much. And so what you do is, for protecting groups of ketones and aldehydes, is you just make an ether with an alcohol. Amines, actually, hopefully at this point, it'll make a little bit more sense. So you had a table in the previous unit that talked about the stability of different carboxylic acid derivatives, and you were asked which ones would cause reactions. And acyl chlorides are the least stable carboxylic acid derivatives, and amines are the second most stable, right above carboxylic acids. So the driving force here is just to get rid of that acyl chloride. So all the protecting groups of amines are just acyl chlorides that are used to kind of form this carboxylic acid derivative. So if I write it more like this, that's all you're forming. Now these are really easy to break, because if you add something like a hydroxide and heat it up, or you add an acid and heat it up, you'll form the carboxylic acid and recover the amine. So it's just exploiting differences in stabilities. We take a really reactive carboxylic acid derivative, make the amide, which is the second most stable carboxylic acid derivatives above carboxylic acids, and then finish it off by making the carboxylic acid. Now, the big thing here with nitrogen, if it's only got one hydrogen, it typically can't do much. So even with like nitrous acid, HNO2, the best thing you can form is like an NO2 group hanging off of it. Will we have free responses? Nope, purely multiple choice. $30 multiple choice questions. Should have plenty of time. Review of basicity. Basicity of what? Because there's lots of things we can discuss basicity. If you're referring to amines, we can talk about that. Figuring out which group is more basic. Yes, amines. So, amines, This is not a universal trend, and so you'll definitely find things that contradict this. But generally speaking, we'll start with NH3. This is going to be our baseline. What makes NH3 a base are these lone pairs. So if we want to make it more basic, what we need to do is add electron density, and this is adding alkyl groups. Pretty much. So if we have a primary amine, naming is fair game. Yes, but not as much as you'd think in terms of the percentage of the exam. So adding more alkyl groups, replacing the hydrogens, that just puts more electron density into nitrogen. The way we make it less basic is we can make it electron withdrawing groups. So we add things like carbonyls. Amides are a good example of something that isn't particularly basic because you have that carbonyl carbon. Now the total extreme is not basic at all. And the way we do this is we get rid of the lone pairs. Now we're not literally getting rid of them, but the easiest way to do this is to make the lone pairs part of the aromatic ring. So if we consider two examples here, pyridine and pyrrole. So here for pyridine, the lone pairs aren't used in the aromatic ring at all, so they're available for accepting hydrogens. So this is a basic molecule, and it's actually pretty basic because we have a lot of really aromatic groups. This is not basic at all. And the reason it's not basic is that if we look at the ring, we have our two bonds here, and then we have our lone pairs up here. Well, if these end up getting used to hold on to hydrogen, we break their aromaticity. So this nitrogen would rather stay like this by sheer merit of the fact that it's got the lone pairs here occupied up in the aromatic ring. Ether reaction, sure. So there's only two ether reactions. One is actually useful, the other is this esoteric academic thing. Anyway, the most useful one is acid catalyzed ether synthesis. It's a reversible reaction. Best used for symmetric ethers, but that said, practically what they do is they just run asymmetric ethers and distill them. Because this is reversible, you can always back change. So let's say you had ethyl propyl ether. Yes, you will get a mixture of diethyl and dipropyl. You can always distill those off and just rerun the reaction to get higher yields. The other is the Williamson ether synthesis. Now, okay, so the major limitation with this is it does go through a carbocation intermediate, so it's not particularly great for primary. You can get rearrangements. But that said, you can make dibutyl ether just fine in the lab. So the other one is the Williamson ether synthesis. With this one, you typically are looking at a bulky alkyl halide and a long linear alcohol. This is not reversible. This is driven by sodium. This forms an alkoxide, which attacks by SN2 and ends up generating the ether. This is not particularly a useful reaction. One, sodium is expensive. Two, like, alkyl halides are really not particularly great for reactors. So this is nice for lab scale bench synthesis, but this is the far more useful reaction. Self-condensation of diols. So I think are you referring to like diols like reacting to form like bigger molecules? So something like that. Mechanisms, elimination primary amine with dichloroalkene. Oh, you're talking about Hoffman elimination. Thiols, don't worry about those. So with these, actually, you kind of already know these. This is how sugars are formed. So if you look at any sugar, so let's say we have like a monosaccharide, they all undergo this acid catalyzed, granted it is enzymatically catalyzed, reaction to form your disaccharides. So that's how polysaccharides are formed in your body. You just take the OH groups, you acidify, and you end up forming these bridging, taking these alcohol groups. They undergo acid catalyzed ether condensation with themselves, and you start building up bigger and bigger chains. So the mechanism for elimination of alkyl halide chloral halide. Okay, so if we have any starting alkene, and typically we're going to see this with chloromethane. The nitrogen will attack the chlorine, break the chloride off. We temporarily end up with a ammonium salt. And then the chlorine, I think it's so weird how chemists write this, pulls the hydrogen off, and we end up generating this group. And we just keep doing it over and over again. This lone pair of nitrogen is just going to keep pushing the chloride off until we end up with a quaternary nitrogen atom. So this reaction is going to occur 2 more times. And we're going to end up with the chloride salt. Now this on its own isn't particularly useful, but if we throw some silver in there, and this is a transition metal catalyzed reaction, so there's a lot more going on that Lewis theory really can't describe, we'll get what's called the Hoffman elimination. Now the Hoffman elimination is kind of like an anti-Zaitsev reaction. So with Zaitsevs, you always eliminate from the most substituted hydrogen. With the Hoffman elimination, you actually do with the least substituted. And the big reason is that this silver needs to get a hold of it. And the silver itself, we're not going to get too much into the structure materials, but you're going to end up seeing basically a structure with a whole bunch of silver atoms on it. This part of the molecule is too bulky to access the surface, but this isn't. And so we'll actually end up getting that type of elimination. But yeah, this is where you stop if this is all you do. And this is kind of a finicky thing with amines and any type of halogenated alkyl groups, is they'll just keep popping off the halogens and constantly eliminating them until you end up with these ammonium salts. And typically when you order like nitrogen containing complexes, it's not uncommon to see them like with HCl, something to kind of get them into the salts to kind of dull this reactivity. But once you throw the silver 1 oxide in there, that's when you end up generating an alkene, particularly one that follows the anti-Zaitsev rule. Instead of eliminating from here, it'll eliminate from here. And again, this is primarily due purely by merit of steric hindrance. Any last minute reassuring words of wisdom, particularly with the 252 final? It's not that bad. So with 251, there's a lot more to worry about. The questions aren't particularly well worded. But with 252, I think the questions are the other extreme. Like the exam is really when you see it, you're gonna notice like there seems to be a lot of repetition with the questions. If you understand question 1, you will probably understand the next 6 or 7. Not sure what your question is. Mechanism synthesis azomethine free. Yes, it will be a lot more. Okay, it'll be different than the 251 exam. I'll put it that way. So we all have to give the same 30 questions on the final. We can add questions to the final, but we can't take out those 30. So all students across all campuses for 251 and 252 see the same question. This is of azomethine from dichloroalkene with primary amine. Look up azomethine really quick. So I'm guessing so azomethine is this complex here. So if you've got a dichloro my guess is you get the first elimination there. And then your lone pair can kick up to get rid of the chloride. And then if you still have this left over, you'll get a subsequent attack by that lone pair to give you the salt. So the mechanism, best guess here, is that you're going to do, the nitrogen is going to pull off the chlorine, the lone pair is going to knock off the second chlorine. That'll give you the nitrogen double bond, and then that lone pair will pick off another chlorine, and that'll end up getting you the azomethine. I mean, another option. I mean, it could attack the lone pair, but that would be such a weird reaction. Okay, so another option is that it attacks the double bond. That kicks the bond up, gets rid of your chloride. But then I think you're kind of dead in the water for the reaction, because there's no reason why nitrogen would subsequently attack that and break the chloride off to form a triple bond. Yeah, there's really no reason it would want to do that. You'd end up forming a really sterically hindered ring. Yeah, I don't know why you would do that. All right, so that's it for the review session. If you got questions, please feel free to email. I can do that really quick. So there is a mechanism for this. I do not think the mechanism is particularly useful. LiLAH4 is a great reducing agent, and what it does is it converts your nitro group into an amino group with a lot of water. When it's all said and done with. Again, there's kind of a mechanism here for this. I think it's it's one of those you'll lose the forest in the trees kind of like mechanism. It's just way too much detail. But overall, lithium aluminum hydride is fantastic for reducing pretty much everything except alkenes. It won't add hydrogens to alkenes. Exams are admittedly busy for instructors, particularly tomorrow. I need to get the grades up. Monday, I need to grade everything, get grades up. I also meeting 3 o'clock Monday afternoon. Tuesday, the plan is Tuesday to have the grades submitted by about noon. This is for your convenience. Our system lags, so if I submit it at noon, this means it shows up by Tuesday night. If you have an issue, that gives me time Wednesday morning to submit any type of grade changes. So check for your grades posted to WebAdvisor. I think it's 6:30 is that when they said when the system would kick over. Again, I could submit them Tuesday afternoon, but the earlier I get in the system, more likely it is that it's actually going to kind of like follow through. So grade changes, you're going to have to be quick on this. The plan is to have the exam grades posted right after you take the exam if I can do it. So definitely by Friday afternoon, those exams grades will be posted. By Monday afternoon, those exam grades will be posted. If you have questions or concerns, email them pretty quick. I'll try to be accessible this weekend, but I do have a life outside of the classroom. So, but again, as far as like grade changes are concerned, yeah, you're all welcome. If you're a point away, you might have room for contending. That said, if you're a point away and you haven't submitted all the assignments, I'm less inclined to give that. If you're a point away, if you're like an 89, there might be some wiggle room. If you're like more than a point away, I'm probably not going to entertain a grade change. So if you got like an 87, I'm not bumping you up to an A. Like that's a solid 87. But definitely a point, there might be some wiggle room. And again, if you've tried everything in the semester, I go through grade board, there's no zeros. Like, okay, I could see maybe re-looking at an assignment or two. But other than that, I will see several of you tomorrow for the exam. Good luck tomorrow. Good luck to y'all Monday. Again, pretty busy for us as instructors right now. If you need to reach out, email is probably the best way to do it. All right, I'll see you later.